And next, we talk about descriptive stats. Very simple, very simple. It's already built in with one simple dot describe function. We immediately get how many data items are there. Obviously, because it's data frame, they should all be the same. And then the average per column for column B, C, and D, the standard deviation, minimum, first quartile, median, third quartile, and maximum, right? So, quickly we get this. Now, remember that this describe, like very simplistically and instantaneously gives us this whole bunch of statistics ready for us to pick and choose. It's like a menu, buffet menu, right? So it's up to us to pick them out and print out a nice report to the user. How do we extract out? Because while printing it on the screen looks good, right? End up we have to eyeball it. What is the average of column C? Maybe column C is number of children, right? So we look at it. Oh, four. Average is four. Um, what is the average number of years of study? Maybe that's column B. So average is 4 and 4.57 years. So we have to eyeball it, and that's not very good. How do we access this particular number 4.57? Well, because dot describe returns this, not surprisingly, as a data frame, and the way it looks is that the columns are BCD from here, all the numerical columns. The indexes, the index values are not 0, 1, 2, 3, but reset to count, mean. Yes, the index values can be labels, can be text strings. So it can be 25%, 50%. And so it makes it quite simple to access um, any part of this data frame using .log, .ilog, at the usual stuff, and so on. So we can extract the B set of statistics and then put a square bracket, quote min, unquote, and then that will select the one. Or quote STD, unquote, then that will be 2.69. So very simple to extract any part of it. And there's one interesting function supported by pandas in the statistical calculation category. That's called n unique. And it's not nonique or whatever. Don't pronounce it. It's n just tries to indicate how many. So how many unique values are there in that column. So it returns a series indexed by the column names and tells us the number of unique values in that column. So if your column has, for example, 7 cells and you have 6 unique values, then you know one of the value is being repeated, like 3 here, right? Okay. And for A, we have X, Y, and Z, obviously 3 unique values. And this is pretty nifty, very useful when it comes to various calculations. It's seldom going to be the final value that's reported to your user, to your application, but it is useful in the intermediate calculations. So keep this in mind. I found this very useful. Now, if you don't have this, you will have to really count by yourself, and that just is irritating, right? So fortunately, we have n unique here. Keep that in mind because I always find it a challenge to remember this nanic function name and unique and unique. How many unique numbers values are there? Next up is the cumulative kind of calculations, stacking up the values. So it goes something like this. Let's just look at the cumulative sum, right? Cum sum. So we make a copy and change A and all that stuff. And when we perform cumulative sum, it sort of goes like this. Remember that if you do a dot sum, it adds across the rows column wise, so we get column sums. So when you do cumulative sum, it's also column based, starting with the first row 0, 0, 0 plus the first row's value 368 plus the second row's value, you get 10 cumulatively, 9, and then 13. Then plus the third row's values, you get 13, 13, 14, and so on. You keep adding more and more. So rows below are always not smaller than rows above. So if you add a bunch of zeros, it's just going to copy the values continuously downwards. but if you have non-zero values, it will stack up. Oh, but of course, if you have negative values in your data, then it may get reduced. So it just adds. All right. No matter what is the sign of the value in your source data frame, it will just keep on cumulatively pile up. Okay. So once we understand this cumulative sum, then a few of the variations come in. What if I want to go horizontally, right? So I want cumulative sum row wise, say, right? Just drop the cumulative, and then you remember that dot sum. If I want row summation, just insert axis equals to 1. All right, insert axis equals to 1. So cumulative sum, same thing. Just insert axis equals to 1, you will get extra column that is not inserted back into DF9 but reported as a new series. So likewise, what do we have? Find a cumulative product, right? So this is the same as cumulative sum. Of course, the calculations are different, but I mean, in terms of the calling mechanism and the expected behavior, it's the same. So going from first row to the bottom row, starting with 111 times 368. So we get 368. Then times 735, we get all these. Keep on getting bigger and bigger, right? But the interesting thing is this, as we go along, the moment it hits 0, right, of course we'll get 0, right? And then after that, 0 times anything is going to be 0. So this is a good example to show that we don't necessarily always expect it to go larger and larger. And another interesting thing is that if your source data has plus and minuses peppered everywhere, then it may go like sometimes bigger and bigger. Suddenly it goes very negative and then goes very, very positive and so on. So make sure you know what you're trying to do before you run all these cumulative calculations. Now, beyond that, we can have cumulative minimum, cumulative maximum. And while this is a little bit new and strange to some of us, including myself, it's kind of not surprising. So we start off with itself, 368 is the minimum. Next row, is there anyone who is lesser than me? 7, no. 3 is lesser than 6, so I keep 3 and throw away 6. 5 is lesser than 8, so I keep 5. So it's kind of like keep on going towards the minimum or even negative. So -1 is lesser than 0, so I go -1. So keep on going towards the smallest, and the last row will be the smallest of them all, right? Yeah. So the last row will be the min of the entire column. And likewise, we can go cumulative maximum. So the last row is the maximum. Okay, next up, we often need to calculate frequency of the unique values. So remember the n unique function. The n unique function gives us how many unique values there are in the particular column. And then we can do frequency. That means for each unique value, of course, minimum is 1, right? Because you are one of the unique values. So, but then the rest, uh, how many counts, exactly. And we can just do a dot value counts. Value counts. Now, of course, this looks a little bit new to us, having an underscore. And that's just it. But it's very powerful, very, very useful. So DF9A, that particular column, all right, with 3 unique values, we do a dot value counts. It straight away returns a new series, giving us in the meat of it, the series contains the frequency. So very, very useful because if you're talking about histogram, this is basically calculating the histogram values without drawing the picture. Yeah, because we don't necessarily always want to draw the histogram diagram, and we do want to know the frequency. Okay, so that's for A. And then for B, for column B, I'm showing A because it's text string. Text string can also have unique values, right? So we can still do it. And of course, text string can be in cases of applications where you say how many people are called John, or how many unique alias names, Christian names are there in my membership database. Okay, if I want to run a contest, how many times, how many members in my membership database are called John? So just to make sure that I'm not overly biased towards certain names. So you can always run this. And then we have frequency count for obviously other data types like integer. This is also kind of useful. And when we run this, we get a series. Basically, we get a sort of a table list of the frequency. That's nice, but it's not necessarily always sorted in the way we want. So we can, especially for numerical unique values, we can ask for the return series to be sorted. So we, in addition to dot value counts, put a dot sort index. Remember, it's a series, so there's an index and the cell value, right? So the dot sort index will return the series with the index values sorted. If it is an integer, obviously sorted. If it's a string, it's sorted based on alphabetical order. Actually, it's ASCII order, the American Standard Code for Information Interchange, based on the code that is assigned to the letters. But to us, most of the time, it will look like alphabetical order. But if we don't want it to be sorted based on the index values, because for example, in highlighting significant occurrences of crimes or significant purchases in an e-commerce shop, right? High frequency transactions for certain accounts. Which account for a bank application? Which account has the most frequent in-out, withdrawal, deposit, withdrawal, deposit? What's this guy doing, right? So to identify such high frequency values, we don't want to sort by the account number. We want to sort by the frequency. And so the way to do it is simply dot sort underscore values instead of dot underscore index. That's all. Very simple, right? So if we sort by values and if we insert I think it's a reverse or equals to true, then we'll get the reverse back. So with this, if we do a square bracket -1 to select the last cell, we will get the highest frequency index and also the frequency itself. So that's nice.